Okay, well, welcome everyone, and we are lucky today to have Ori Adam, who is here on a sabbatical for a year after just getting his tenure there at the Hebrew University of Jerusalem. He got his PhD there in 2016 with Nathan Paldor, and if Arthur was on, I'm supposed to say hello from Nathan Paldor, and went off to postdocs in Tel Aviv and in Zurich when Tapio Schneider was there, and now he's back at HUJI there, Hebrew University of Jerusalem, and as a professor and academic head of the climate group and also the research computing facility there. And he's going to tell us today about some of these energy equator energetic arguments that he's been working on for quite some time here, as the bibliography shows.
Okay. Okay, so thank you for inviting me to speak here today. And as Brian mentioned, I'll be here through the academic year, so I'll be happy to discuss further the ideas I'll be presenting today and others as well. And my sabbatical here is Dean Roni Avisal on a completely unrelated topic, but I'll be happy to speak about projects related to Roni Avisal as well whilst I'm here. And what I'm going to talk about today, I'm just going to touch on various topics from recent publications of mine and some still in preparation or submitted, all revolving around the idea of transitions from single to double ITCZs in the tropics. So let's just dive into that. Okay. So what is an ITCZ, an intertropical convergence zone? So suppose we're in an idealized planet where there are no continents and just a simple ocean. The tropical rain belt would look something like we're seeing here in this plot. It would be a zonal band of precipitation that lies along the rising branch of the Hadley circulation. And this is actually taken from an aquaplanet, the NPI. And the ITCZ, the intertropical convergence zone, would be co-located with the latitude where the equatorward flowing surface winds of the northern and southern Hadley cells converge, rise, and precipitate, and so forth. And so this would be very consistent with the Hadley circulation paradigm. However, in the present climate, because of all of the symmetry breaking mechanisms, continents and other stuff that's going on in the real world, the distribution of precipitation in the tropics is not like what we would expect from a simple Hadley circulation paradigm. And specifically, as you can see in the Western Pacific, for example, there are double ITCZs on either side of the equator, and this is inconsistent with a Hadley-like thinking, because a Hadley-like thinking only accepts a single ITCZ that follows the sun in its seasonal migrations. So there's something else that's going on here, and this is and I'll be essentially trying to explain some aspects of the distribution of precipitation in the present climate and perhaps other climates as well. And we can also look into past climates. So this is, for example, from simulations using the HUJI model with collaborators of mine in Bristol University, where they've done a sweep of simulations where you change the configuration of continents, you fix everything, and you just change the configuration of continents going from 300 million years ago to the present. And as you can see, there are some climates that look similar to what we have today, but in some climates where you open up the Paleo-Pacific, you get these very dominant double ITCZs on either side of the equator, which looks nothing like what you would expect from a Hadley circulation. So it's important to understand these dynamical regimes as well. And so I've shown you an example from past climates, but also even in the present climate, during the seasonal cycle, so during boreal spring in the Eastern Pacific, when the Eastern Pacific cold tongue is warmest, a double ITCZ emerges, two ITCZs that line up along the equator. So these variations from single to double ITCZ occur on seasonal to geological timescales and also across regions. So what I'll be talking today about is trying to understand these types of variations. Another important example is that, as I said, the ITCZ in the Hadley paradigm follows the sun. So you would expect the ITCZ to migrate towards the warming hemisphere, but this is from Armstrong et al., but it's essentially the same, a simulation for the same suite of simulations using the HUJI model. So in this simulation, during the real summer, the dominant ITCZ is closer to the equator than during winter, which is completely counterintuitive to the Hadley circulation paradigm. And usually when we try to interpret paleo records, we assume that the precipitation bands migrate towards the warming hemisphere, but that's not necessarily the case in the seasonal cycle in past climates that are dominated by double ITCZs. Another interesting topic that motivates research of transitions from single to double ITCZs is the notorious double ITCZ bias. So shown here are in black contours are the observed precipitation, and in colors are the CIMIP 5 ensemble mean precipitation. And as you can see, south of the equator, models tend to overestimate precipitation, leading to an overly doubly picked precipitation distributions, and hence the name, the double ITCZ bias. And this was first shown by Mechoso in 1995, but quite remarkably, the same bias has persisted through every generation of climate models. So with really negligible variation, this is from Tian and Dong, a recent publication, essentially without any variation, the same bias has existed through CIMIP 3, CIMIP 5, and CIMIP 6. So this really suggests that there's some essential physics that is not captured by climate models. And last but not least, this would also affect projections of changes in precipitation in the tropics that also have this double ITCZ pattern in them. So it's important to understand double ITCZs also for projected changes in precipitation. So what I hope what I was able to achieve in this short introduction is to convince you that variations between single and double ITCZs, these types of variations are important and critical for our understanding of the present and past and maybe future climates. And I'll refer to these variations from single to double ITCZ as variations in modality, in the modality of the tropical rainfall. So I would first try to objectively quantify modality. Can we distinguish between low and high modality climates, or is it just descriptive? And then I'll describe some zonally asymmetric mechanisms that affect the precipitation distribution in the tropics, and conclude with zonally symmetric mechanisms. And as you can see, this is a very low resolution type talk. I'm going to talk about really large scale dynamics. Okay, so I'm showing here 3 examples. So the top panel is the present climate from era interim precipitation. The side panels show zonal mean precipitation. And the middle panel is precipitation during the pre-industrial conditions simulated by the HUJI model. And the lower panel is Plains-Bachian conditions about 190 million years ago, again using the HUJI model. And as you can see, in the present climate, it's closer to being a unimodal precipitation distribution, and during the Plains-Bachian conditions, it's a very strongly bimodal distribution. So the question is, can we quantify, can we put a number on how close is it to being unimodal or bimodal distribution, and whether that actually has some significance. And as I'll try to convince you, this actually does matter. It's important to distinguish between unimodal and bimodal distributions when we examine the seasonal cycle of the tropical rainfall and some aspects of the lower scale circulation. So shown here are the same examples and just the zonal mean precipitation. So the left panels show the zone of mean precipitation in bold, and then the solstitial seasons in the thin lines. And then I've decomposed the zone of mean precipitation into, in the middle panels, hemispherically symmetric component, and the right panels, hemispherically anti-symmetric component. And what I'm trying to show here is that it's only the hemispherically symmetric component that has the bimodality aspect in it. And this is because hemispherically anti-symmetric, the anti-symmetric component doesn't affect equatorial precipitation. So it's equatorial precipitation inhibition that creates this bimodal nature of the precipitation distribution. And another thing to see here is that if you look at the thin lines, you'll see that the bimodality persists through the solstitial seasons. So the bimodality is not a consequence of the seasonal migration of, say, the ITCZ. It's really a year-round thing. So using equatorial precipitation inhibition is a good way to objectively quantify the modality of the precipitation distribution.
Can you, are these climatologies for how many years, in which time was that done? I mean, how do you, can you speak a little bit about the data?
So from air interim, it's a 30-year average, and similarly with the HADSIM-3 model, it's a long-term means. I think it's averaged over 50 to 100 years, so it's a very steady state means. And sure, there would be very small variations between, so for example, the air interim data set or other data sets, but essentially, I mean, for the resolution of stuff that I'm trying to show here.
And those are monthly or weekly or daily?
It doesn't matter. When you do the long-term mean, it doesn't matter because you're averaging over several years. So it just wouldn't matter. I mean, and for the kind of stuff I'm trying to show here, it doesn't affect the principle I'm trying to convey, because it is what it is. I'm just trying to show you a situation and then try to quantify how close it is to a unimodal versus a bimodal distribution. So it doesn't really matter in a sense. I don't want to get into the details of how we got to this parameter, but to quantify modality, we're using something called the equatorial modality index, because it's based on equatorial precipitation inhibition. And it's a very simple parameter. It's basically 2 minus some factor, alpha, times P naught, which is equatorial precipitation, divided by the mean precipitation in the tropics, P bar. And then there's this additional term there, the phi cent, which I'll discuss in a second. But without that term, when P naught is equal to 0, EMI is equal to 2. So a strictly bimodal distribution is one where you have 0 precipitation at the equator, and then the modality increases as equatorial precipitation increases. And then this additional term, phi cent, it's the centroid of the precipitation distribution squared divided by 2. Sigma is the standard deviation of the precipitation distribution squared. It's essentially a first order approximation. As I'm showing in the top panel, it's a first order approximation of the change in the value of equatorial precipitation as a Gaussian shifts north or south. So since we're basing our quantification on the value of equatorial precipitation, we want to correct for that value for a unimodal precipitation that shifts north or south. Okay, so this is this correction. And so here I'm showing just examples for hemispherically symmetric distribution or hemispherically asymmetric distribution of high versus low modality states. So this may be just an exercise and maybe meaningless, but it's a nice way, it's a nice parameter that gives you values between 1 and 2, 1 for unimodal precipitation distributions and 2 for bimodal precipitation distributions. So we tested this parameter over a sweep of 45 simulations of paleostates spanning the past 300 million years, again using the HADSIM-3 model. And as you can see, it nicely captures variations between unimodal climates and bimodal climates. And similarly, we tested this over 73 CIMIP models, 42 from CIMIP 5, 31 from CIMIP 6, and it distinguishes between high and low EMI climates, and not surprisingly, the models that have a lower EMI are also the ones that have a lower or a weaker double-ITCZ bias. So since we're basing our distinction of our quantification of modality on equatorial precipitation, this index is strongly correlated not just with values at the equator with other phenomena, but it's also correlated with phenomena in higher latitudes, because equatorial precipitation inhibition is strongly controlled by the overturning circulation. Okay? So then this is what I'm showing here. So this is correlation across the HADCM3 simulated, the 45 simulations across climate states, and then the 73 CIMIP 5 and 6 models. So, and this is the correlation of EMI per latitude with precipitation minus evaporation, which is a good approximation of the vertical wind. So that's what I'm trying to show here, that this index is strongly correlated with vertical wind or the overturning circulation, even in higher latitudes. Okay? And indeed, this index is strongly correlated with, it's negatively correlated with the tropicals to poles temperature difference, with the intensity of the equatorial cold tongue, with the width of the meridional overturning circulation, it's negatively correlated with the intensity of the meridional overturning circulation. It's positively correlated with the Walker circulation intensity, and also positively correlated with the width of the ITCZ, or the width of the rising branch of the meridional overturning circulation. So what I'm trying to show here, that this is a parameter that not just tells us something about the modality is perhaps a more fundamental value that summarizes a lot of our ignorance about the climate state. Okay? It just encapsulates some other properties of the climate state. And I think more importantly, it gives us an important distinction about seasonal variations. So I'm showing here examples from the present climate. So in the Atlantic, we have a single ITCZ, and EMI there is equal to 1. It's a unimodal precipitation distribution. And there, the seasonal variation of the ITCZ there is Hadley-like, or monsoonal. It's not really monsoon, but it's monsoonal in the sense that you have migrations following the sun and sharp seasonal contrasts. However, in the Western Pacific, we have ITCZs on either side of the equator year-round, and there are additional modes of variability. So I'm showing here examples of models with high modality in the Western Pacific from CIMIP 5, and we identify 3 important modes for high modality climates. One is a shift of the precipitation distribution towards the warmer hemisphere. It's not really a migration, it's just a shift of the weight of the precipitation distribution towards the warming hemisphere. Second mode is the variation in the separation between the hemispheric ITCZs. And third, it's a seesaw variation in the intensity of the ITCZs on either side of the equator seasonally. This was also recently observed by Zhao and Fedol in a paper from a couple of years ago. So as a consequence of that, for high modality climates, hemispheric ITCZs do not necessarily follow the sun, as is usually our very basic expectation when we try to interpret paleo results. And the reason is that we can think about the separation, the distance between the hemispheric ITCZs and the migration modes as being independent, and the separation mode can counter the tendency of ITCZs to follow the sun, or even overcome it, leading to a contrast in the shifts of hemispheric ITCZs and the centroid, or the mean tendency of the distribution to follow the sun. So for high modality climates, hemispheric ITCZs do not necessarily follow the sun, consistent with what I showed in the previous introduction. Okay, so just to summarize this part of the talk, I'm arguing the tropical modality is an important climate characteristic that summarizes our ignorance of variations of the tropical rainbed, and we suggest EMI as an objective way to quantify tropical modality. And we distinguish between the seasonal cycle, we distinguish between low and high modality climates. Low modality climates have a Hadley-like monsoonal seasonal variation, but high modality climates have these three modes. And in addition, they're correlated with wider and weaker meridional overturning circulation and a weaker tropics to poles temperature gradient. And these three modes are migration, separation, and seesaw. And as a consequence of that, hemispheric ITCZs do not always follow the sun in high modality climates. So I'll be happy to take questions about this part, and if not, I'll just move to the second part. Okay. So some zonally asymmetric mechanisms. What I'm showing here are in colors are precipitation, and the contours, the black contours, are sea surface temperature in the Pacific. On the left-hand side, I'm showing the precipitation during near the March equinox, where the cold tongue in the Pacific is weakest, and you have these double-ITCZs in the Eastern Pacific. And then on the right panels are showing conditions around the September equinox, where the cold tongue is strongest, and you have this zonally or diagonally oriented ITCZ, mostly north of the equator. And we want to understand these variations because they're critical for to understanding the present climate, but also past climates. As I've shown before, this pattern sort of repeats itself in other climates as well. And a nice framework for understanding tropical variations is what's called the Matsuno-Gill model, after the famous papers by Matsuno 66 and Gill 1980. And this is essentially a shallow water model on the equatorial beta plane. Here, and this is a non-dimensional model, so here y is the Coriolis parameter, v is the poleward, northward meridional wind, and at the surface x and y are zonal and meridional directions, h is the height of the water column, and then epsilon is this damping coefficient that incorporates a lot of the processes that are basically excluded from this very simple linear model. And this model is forced with the source term q, and because of this very simple and redundant model, the vertical wind is essentially prescribed by the source. Okay. And also, because this is a shallow water model, we can think of H as being analogous to temperature or pressure. Okay, so most of the studies of this model have focused on the limit of epsilon going to zero, or the inviscid limit, specifically focusing on tropical waves and so forth, and how we can interpret tropical variations that result from tropical waves. And very few papers have looked at what happens in the viscous limit, the limit of epsilon equal to 1. And as I'll be trying to show here, this is actually a relevant and a very revealing limit of this model. So, so if we rewrite the equations in terms of vorticity and divergence, q is minus divergence, then at steady state we get this equation, so y times q is equal to v plus epsilon, and then vorticity is this psi here. So in the implicit limit, we get something known as the Svelda balance. So upward motion is associated with poleward motion. Positive v in the northern hemisphere, negative v in the southern hemisphere. So this is, for example, why in the Walker circulation, in the rising branch of the Walker circulation, rising air develops a poleward component, and descending air develops an equatorward component. And this is why the Walker circulation is really a 3D circulation, unlike the Hadley circulation, which is a 2D circulation. So this is in the inviscid limit. And in the viscous limit, vertical motion would be associated with this epsilon times vorticity divided by y. Vorticity divided by y is also known as the local Rossby number, but regardless of that, here rising motion would be associated with positive vorticity in the northern hemisphere and negative vorticity in the southern hemisphere, or essentially cyclonic motion. When we compare this with observations, so this is actually taken from observations. This is the first vertical mode of observed annual means. So blue colors are upward motion, the green colors are downward motion, and the arrows show the direction of the surface winds, or actually the difference between surface and upper winds. So consistent with the Sveldo balance, in the rising regions we have poleward motion, but also in the rising regions we also have the development of cyclonic circulation. So it's really hard to say from observations what is the right limit. It's probably somewhere in between, but we definitely cannot say that it's just invisible. Okay, so what I did in this work is I used the original source term as Matsuno, 1966, essentially trying to recreate a Walker circulation by forcing a sinusoidal zonal function that is enveloped by a Gaussian. And the source term is just this relaxation to this prescribed height shown here. But I added another thing, which is I made this into a coupled idealized atmosphere ocean model, in the sense that I added an idealized Bjerknes feedback. So here I've introduced Ekman pumping, so the surface winds drive upwelling along the equator in the ocean, and this upwelling of cold water cools the surface and creates the Pacific and Atlantic cold tongues. And so this cooling can be made proportional to the easterly stress by the surface winds by this coefficient. So by introducing cooling associated with the surface winds, this is essentially an idealized coupled model, where the cold tongue is not prescribed, but it's an emergent feature of the fact that you have easterly surface winds that are associated with the Walker circulation, and hence this is an idealized Bjerknes feedback. So in the viscous limit, as I mentioned, there's a really nice simplification, which is that the equations are simply solved by assuming h is equal to h bar. This is mandated by the viscous limit, and if you know h, then everything follows, and you can actually get analytic solutions for the vertical wind. And interestingly, in the viscous limit, what you get is, so if the blue colors are upward motion, then in the viscous limit you get double-ITCZs along the descending branch of the Walker circulation. So this is an additional mechanism for the generation of ITCZs simply through damping. So this is kind of nice, because this is analytic, and we can easily understand and solve for this. And we can also analytically solve for the contribution of the Bjerknes source term, which looks like this, and then we can combine these solutions and obtain the steady state solution when we have both the Bjerknes component and the Walker component. And this doesn't look that different from the observed vertical wind. So this is kind of nice. So we can now go back to the original question, which is trying to understand the seasonal variations in the Pacific between equinoxes. So again, so what I'm showing here is now the hemispherically symmetric component of precipitation in colors, and then the anomalies in SST in the contours. So around the March equinox, we have a warm anomaly in the Eastern Pacific. So the cold tongue is weakest, and we have ITCZs that are parallel to the equator. And then around the September equinox, we have a cold anomaly in SSTs, and therefore the strongest cold tongue and diagonal ITCZs. And so around the March equinox, what we have is a weaker zonal SST gradient and a stronger poleward SST gradient because of the warmer cold tongue. And then around the September equinox, we have a stronger zonal SST gradient and then a weaker poleward SST gradient. And these variations are actually captured in the very simple source term that I'm using. This is a bit hidden by zoom here, but essentially with this relaxation height, so A is the amplitude of the sinusoidal function that controls the zonal SST gradient, and then sigma in the envelope function controls the poleward meridional gradient. So we can the parameter space of the model actually captures these critical components, the zonal SST gradient and meridional SST gradient. So what we find is that if we plot the solutions along this parameter space, what we find is that this more or less is consistent with the predictions of this very idealized model. So this is a simple model that gives us an analytic, very simple understanding of how these variations in the ITCZ come about as a function of the very simple parameters of the system. Okay, so just to summarize this part of the talk, the viscous limit of the Matsuno-Gill model, in the viscous limit, we have the emergence of double-ITCZs along the descending branch of the Walker circulation, which is a new and interesting, another mechanism for generating double-ITCZs. And then parameterized Ekman pumping yield and idealized Bjerknes feedback in the Matsuno-Gill model, so we can extend the Matsuno-Gill model to simple idealized coupled problems. And then the zonal and poleward surface pressure gradients control the intensity and width of the cold tongue, and therefore also the intensity and zonal orientation of the ITCZs on either side of the cold tongue. And this captures the seasonal variations that we see in the Pacific. And this is all from this paper.
So does this not work in the Atlantic because the basin is too small?
The basin is small and also more complicated because it's engulfed by Western Africa to some degree. The cold tongue is also weaker in the Atlantic, and it's controlled a little bit by a little different mechanism than the Pacific. And the Atlantic is dominated by just a single ITCZ. You don't see an ITCZ in the southern hemisphere, at least in the present climate. So yeah, so this, I guess you could adapt this also. You can try to adapt this also to the Atlantic, but yeah, in essence, you would see something different because the Atlantic is very different from the Pacific. Okay, so third and final topic is zonally symmetric mechanisms for going from single to double ITCZs. So if we, again, going back to the Hadley circulation paradigm, so a single ITCZ would go along with a Hadley circulation or a unimodal precipitation distribution, but then the double ITCZ implies ascending branches on either side of the equator, and therefore also a descending branch at the equator, and this is an anti-Hadley circulation. Okay, so single ITCZs, Hadley circulation, unimodal precipitation distribution, double ITCZs, and anti-Hadley circulation, and a bimodal precipitation distribution. So it's interesting to study the dynamics of how the system transitions from Hadley to anti-Hadley circulation. And a very simple principle that allows us to make sense of this bifurcation from a single to double ITCZ is something proposed by Bishop and Schneider in 2016, and that using the energy balance of the atmosphere. So essentially, the Hadley circulation transports energy from the equator poleward, and energy transport in the Hadley circulation follows the upper branches of the circulation. But then, if we, for example, using equatorial ocean heat uptake, if we increase equatorial ocean heat uptake gradually, then at some point, the energy balance at the equator would become negative, meaning we would create a deficit of energy at the equator. And then the circulation would need to adjust so as to now transport energy towards the equator, because we're pumping energy away from the equator, and then the circulation now needs to adjust. And this is what happens as we increase equatorial ocean heat uptake. We go from a Hadley circulation and we bifurcate to an anti-Hadley circulation. So we can understand the bifurcation from a single to a double ITCZ using these really simple energetic constraints. But this is for a prescribed ocean heat uptake. And
Why don't they call it downtake? Uptake is such a...
It took me a while to get used to the terminology. Please don't change
Yeah.
the terminology. Now it makes sense, but I concede that, I mean, some of the terminology is a bit esoteric. So net energy input into the atmosphere is the key parameter here, where when it's negative, we would expect double ITCZs. When it's positive, we would expect a single ITCZ. And indeed, as we can see here in the Pacific and the Eastern Pacific, where the cold tongue is strongest, that's where we have a negative net energy input into the atmosphere, and that's where we see the bifurcation to a double ITCZ. And finally, this is what really the topic of that publication. We also have to take into account the fact that this is a coupled system. So we cannot just prescribe the intensity of the cold tongue. The cold tongue itself is an emergent property of the circulation. So if we change the circulation, we also affect the cold tongue. Okay. And what I show in this paper is that there's this interesting negative feedback, because in the Hadley circulation you have easterlies, and these easterlies you have easterlies along the equator. These easterlies drive equatorial upwelling that creates an equatorial cold tongue that can lead to a bifurcation from a Hadley to an anti-Hadley circulation. But then the surface branches of the anti-Hadley circulation have these geostrophically balanced westerly components. And this now damps the easterlies, which damps the equatorial cold tongue, and therefore an anti-Hadley circulation cannot intensify, because it kills the mechanism that produces it. So this is a negative mechanism that suggests that anti-Hadley circulation is limited. The intensity of the double ITCZs, and also the separation, the extent of the anti-Hadley circulation is limited by this negative feedback. And to show this, I'm using this intermediate complexity model. So this is from simulations using an aquaplanet, a simplified version of the NCAR GCM with a slab ocean that has in it parameterized Ekman energy transport using the Quadron 2012 scheme. So essentially you have a GCM with an ocean component that just has wind-driven ocean circulation or energy transport. And the parameter that I'm changing here, alpha, is this parameter controls the stratification of the ocean. So when alpha is equal to 1, the stratification is 0. And so even if you have equatorial upwelling, you're not really mixing cold and warm water, because there's no stratification in the ocean, so there's no equatorial cooling. But as you increase the stratification of the ocean, you begin to develop an increasingly colder cold tongue. So for alpha equal to 1, you have this unimodal precipitation distribution, and these simulations are for hemispherically symmetric conditions. So you begin with 1, a unimodal precipitation distribution, and then as you decrease alpha, or you increase the stratification, equatorial precipitation quickly decreases, and you develop these double ITCZs. And then if you look at the lower left panel, this is the vertical wind. You see that at some point, the vertical wind becomes negative, meaning we've bifurcated into an anti-Hadley circulation. But unlike the decrease in vertical wind for the Hadley-like case, when we go into an anti-Hadley circulation, despite increasing the stratification of the ocean, the vertical wind doesn't become more and more negative because of this negative feedback that doesn't allow anti-Hadley circulation to intensify. So it's very limited. Another way of seeing it is here in the surface zonal winds. We see that the zonal winds weaken as we increase the stratification or increase the intensity of the cold tongue. Again, because of the development of the westerly winds associated with the anti-Hadley circulation. And another interesting aspect of this is that if we associate the edge of the Hadley circulation or of the meridional overturning circulation with the latitude where the easterlies change into westerlies, it's a common index for the width of the meridional overturning circulation, then we see that as modality increases, going from 1 to 2, or as we increase the intensity of the cold tongue, the meridional overturning circulation widens, consistent with what I've shown before. And since this is a zonally symmetric mechanism, we can actually use axisymmetric theory to examine it further. So it's a really nice exercise to take the very classical Hadley-like model, and for those not familiar, it's a very simple model where you assume axial symmetry, so there are no variations, there are no zonal variations, and you also assume steady states, so there are no transient or stationary eddies. And then if you assume conservation of angular momentum in the tropics and conservation of energy as well, you can actually obtain analytic solutions for the extent of the Hadley circulation and some other properties. And so it's a nice exercise to take the Hadley-like model and then apply equatorial cooling and see what happens and solve for how the extent of the Hadley circulation changes. What I find here in this exercise is that as you increase equatorial cooling, the edge of the Hadley circulation actually draws close. The Hadley circulation narrows instead of widening in the full GCM. And what this implies is that eddies are actually also important for these transitions from Hadley to anti-Hadley circulation, or for variations in modality. So it's not just about what happens in the equator. So let me summarize this part of the talk and essentially conclude the talk. So double-ITCZs and their associated anti-Hadley circulation emerge due to equatorial cooling in coupled models. We find that the negative Ekman transport feedback limits the intensity of anti-Hadley circulations and therefore also the intensity of double-ITCZs. And probably eddies are also important for understanding variations in tropical modality. And then for this whole concept of variations in modality, I think there are some interesting remaining outstanding questions, which are the role of eddies, as I've just shown, the role of convection, the relevance of these circulations not just to this planet but to other planets, and also maybe whether this framework of thinking about these variations in terms of modality can shed light on the double-ITCZ bias. So thank you for listening, and I'll be happy to take questions.
Sounds like everything matters. And if you go off to models, the convection scheme matters. If it couples to inertial mixed Rossby gravity waves, then you get more double-ITCZ. And I think people have even shown that the time step matters in a model. You change the time step and your double-ITCZs become single or wider. And
So
it's such a delicate feature.
Yeah,
How do you deal with that when you're looking at these models? You just get the outputs of the global modeling enterprise. You don't quite get to play with their time steps.
Yeah, it's true that the convective scheme, you can get transition from a single to double-ITCZ just by changing the convective scheme. The nice thing about the energetic framework, though, is that regardless of whether it's due to convection or just due to dynamics, the energetic framework still applies. It's still consistent with the shift from single to double-ITCZ. So the energetic framework works even if what's causing the change is the convective scheme. It's still consistent with that. But it's true that there's a wide array of mechanisms here that could affect the modality of the tropical rainbed. But nonetheless, if due to convective parameterization you do the double-ITCZ, this change in what I call tropical modality, I think still tells you something about the system. So even if it's due to convection, a higher modality system would still have these characteristics that I've just shown: a wider MOC, changes in the seasonal cycle of the tropical rainbed, and so forth. So I think, again, this is a very low resolution type of thinking that gives us intuition at best, but I think it is helpful to think about how it affects the tropical climate, regardless of the specific mechanism.
Sorry.
No, you go.
Can you explain something about the South Pacific convergence zone, which is, I guess, not axisymmetric.
So, what you're referring to is this thing here. So,
Or can you repeat the question for the
so the
Zoom
question
audience?
was about the South Pacific convergence zone. So this lobe here is called the South Pacific convergence zone, and I hate the term, by the way, because to me it was like, okay, we think we understand this because this would be associated with the Hadley circulation, and then we have this thing here that really is dissonant with the concept of a Hadley circulation. Let's just give it a different name. Let's call it an SPCZ, and then we have the ITCZ, which is this, and this whole different thing, which we call the SPCZ. I don't like the term. I think it's part of a single pattern. Okay, but this is what we call the SPCZ. I think Trenberth called, and a bunch of stuff that are affecting the SPCZ. There's the decay of subtropical storms in the region that cause precipitation. I think Trenberth called the SPCZ the graveyard of subtropical storms or waves. So there are the turbulent aspects that affect the SPCZ, and there are some really interesting dynamics. But I think essentially, and I forget the name of the person who published, come back to me in a second. In essence, the SPCZ, I think, should be perceived as this bifurcation of the tropical rainbow caused by the existence of the cold tongue that creates this cleavage in the precipitation, and that leads to a peak in SST on either side of the equator, and precipitation tends to lie over regions where you have a peak in SST. So I think that's the essential feature that drives the existence of the SPCZ, and then there are additional mechanisms such as the effect of subtropical storms and other stuff. But to my understanding, in essence, the SPCZ is not really different from the ITCZ north of the equator. It's part of this single pattern where you have a cold tongue that basically creates ITCZ on the other side of the equator. And it turns out in the present climate, the northern hemisphere is warmer than the southern hemisphere, so you have this additional bias towards the ITCZ north of the equator. But I think it's part of this uniform pattern, not an independent aspect of tropical climate. But I have to say, this is my interpretation. There are other people who think otherwise. Yes, please.
This kind of relates to that then. What's your interpretation of the so-called SPCZ in the pre-industrial panel there being quite a bit stronger than now and stronger than the ITCZ?
Yeah, I mean, as I said, the HUJI model is, I think it's a really simple model, but I think it's quite remarkable in it's a sort of a first generation climate model. So it's simple, so it's very crude, but because it's simple and crude, you can run it efficiently over a wide range of climates. So this is why it's commonly used for asking paleo questions. But as I said, it definitely has a bias. It's a fully coupled model, and it has a very strong double-ITCZ bias, and this is the manifestation of the strong double-ITCZ bias in the HUJI model, definitely.
Amy Clement.
Yeah, Amy?
Okay, hi. Sorry I can't be there in person to eat the cookies, and I promise to help out on that another time. I'm good at that. Great talk, Ari. I wanted to circle back to Brian Mapes' kind of line of questioning and challenge you a little bit more on this concept of this framework, which I think is, I understand it's like really satisfying to be able to put all these pieces together in an understandable way, but how does it get us to practical ways to think about the correcting the double ITCZ bias, or does it? Can it?
That's a good question. I have to say, it's something that I am working on. one aspect is that when we think about the double-ITCZ bias, for example, it's also a seasonal bias. It's not a bias in the end. It actually has a year-round component, but actually most of the double-ITCZ bias is seasonal. So most of it occurs during the southern hemisphere rainy season. And it's essentially the part that we focus on occurs because the ITCZ in the Pacific in climate models tends to migrate further south than in the present climate. And perhaps if we have a better understanding of the seasonal variations of the ITCZ and the mechanisms that explain seasonal variations of the ITCZ, then we'll be able to better explain what's going on with the double ITCZ bias if we have a better understanding of seasonal variations. I'm not saying that I have the answer, but I think it just must throw us in the right direction. That's one.
Okay.
And secondly, also, the ITCZ is a coupled model problem. It doesn't exist. There are components. There's so many theories, so many papers written on the double ITCZ bias, and some link the double ITCZ bias to inherent biases in the atmospheric component, but it only appears in coupled models. So it's also important to understand the coupled system, which is really hard to do. So using idealized models to understand the coupled system, I think helps us or brings us, some steps forward in understanding this. It's essentially a coupled model problem. We cannot just isolate the atmospheric source or the oceanic source or just the convective source. It's a really coupled model problem, and I think we have to use idealized models and concepts to get us at new ideas. So that's my take on that. And I am working on this. I have some ideas that I'll be happy to share. But I agree. This is a very low resolution, intuitive tool. Nothing more than that.
Okay, well, I look forward to more discussions on that over the next year. So thanks.
Thank you.
Any more questions from the room? If not, thank you for the nice presentation. Thank you for coming in person, and thank you for coming in Zoom. And we will continue next Wednesday with Amy Dobracki's 1 hour seminar. And I heard that Paquita still needs to review the abstract, and then we will send the email about it.